Hi, it's Tim. Welcome to the corner. Today we have got some chips to test. These are UM6507 CPUs, and they are the CPU that is used in a Atari 2600, for example. So, not having a 2600 to do a swap out test in, we're going to have to design a tester to test these chips. So let's do it. The main difference between this and a regular 6502 is that it comes in a 28-pin DIP package rather than a 40-pin DIP package. And a very similar variant of this, the 6504, is used in some Commodore disk drives. Now, I got these chips for another project. They came from a wholesale Chinese supplier, and I need to check whether they work or whether they don't work, or even whether they're fake. But not having something like an Atari 2600 to substitute them, we're going to have to build a tester from scratch, and we're going to use a few resistors and capacitors and some LEDs and a 555 timer. So let's do it. A quick word about our sponsor PCBWay. The board that we are using for today's project is a prototype board, and it's actually a prototype board for a Commodore 64. This came from PCBWay. We're not using it as a 64 prototype board, but in theory we could actually plug this into a C64 and wire it up and talk to the 6507. This board is a shared project. Shared projects are from people that have designed their own PCBs and made them available for the wider community. They also do PCBs from your own designs, such as these. They do other things as well, CNC machining and 3D printing. You can have your PCBs UV printed in multiple colors, any design you like. Very pretty. Check them out, www.pcbway.com. As with a lot of MOS processors, the 6507 was licensed out to other manufacturers, and these are made by UMC, so the part number is UM6507, and it appears to have a date code of 8747 on that one. Some of these are a bit hard to read. Anyhow, so what is a 6507? Well, it's a CPU in the 6502 family, and it has 28 pins, 14 down each side, and they're going to look something like this. Right, so that is pin 1, that is pin 28, pin 14, and that is pin 15. So we've got reset signal coming in here, that is ground. We have a ready signal here. On the 6504, that is actually IRQ. That is the primary difference between the 6504 and the 6507. That is VCC, and then we have address lines A0 all the way down to A9 and A10, A11, A12 on that side, and that's all the address lines that we have. We do not have A13, 14 and 15. So basically this can only address 8K. Then we have D7 all the way up to D0. That is read write. That is Phi 0, which is our clock input, and this is Phi 2, which is our clock output. So that's basically our 6507. And what we need to do to test this is set NOP. And that is going to be basically set on the D0 to D7 data lines. And that is hex EA. So the idea is that if we set EA on the data lines and we fire off the clock, then that is going to do a NOP at every address. And NOP means advance the address register to the next address. So it should see all the address lines cycle through. And it's going to start from FFFE, I think, because that's where the reset vector is. But we should see it go FFFE, FFFF, 0, 1, 2, 3, and so on. So how are we going to build our tester? Well, right, so one, we need to, and that is going to be 1, 1, 1, 0, 1, 0, 1, 0, from D7 to D0. And to do that, we are simply going to take the pin, put it through a 1K resistor, and then that will either go to ground or it will go to VCC, one or the other, depending on which pin it is. We also need to tie some of our signals to 5 volts to VCC, and those signals are reset and ready. And again, we are going to do that through a resistor. This just simply so that we get a certain amount of current protection in there. And then we're going to look at the address outputs, because that's what we want to see. Now we can look at that using an oscilloscope, and that would be fine, but it's more fun to have a nice little display. And so we are going to put some LEDs on there. And how many LEDs we use is going to depend on how fast we clock it, because the faster we clock it, the less useful the low address bits are. So A0, A1, they are going to be the fastest to clock, and if you're running at, say, 1 megahertz or 100 kilohertz, that might not be useful to look at those, because you won't be able to see them flashing. On the other hand, you'll be able to see if they're not doing anything. But we are basically going to, again, put them through an LED and a 470 ohm resistor down to ground. We can use kind of almost any value resistor here going upwards, depending on how bright we want the LEDs to look. So 470 ohms, 1K, it also depends on the LEDs we use, but that's a ballpark figure. And now we come to the clock. For the clock, we're going to use a 555 timer. So let's draw us a 555 timer. And we're going to use it in astable mode, so this is a fairly standard circuit. Pins 4 and pin 8 go to VCC. Then we're going to take the ground, pin 1 goes to ground, and pin 5 goes to ground through a 10 nanofarad capacitor. Pin 3 is our output. Okay, so now to control the frequency of it, we are going to use some resistors and capacitors. So we're going to have a voltage divider essentially here and a capacitor here, like that. Now this point here goes to pin 7. This point here goes to pin 6, and we are also going to connect it to pin 2. So that is our astable 555 timer. We just need to set values for R1, R2 and C1. We also need a capacitor between voltage and ground. Standard decoupling thing. Right. So the values that we have chosen are going to depend on the frequency that we want. So we're going to start with this at being 1K and this at being 6K2. Then if we want 100 kilohertz, so that's 10% of the clock speed, it's basically as fast as a 555 can run comfortably. That is going to be 1 nanofarad. If we want to slow the clock down, we can do that simply by changing the value of C1. So C1 equals 1 nanofarad. That gives us 100 kilohertz approximately. If we make that 10 nanofarads, then we get 10 kilohertz. I'm sure you can see a trend here. 100 nanofarads will give us 1 kilohertz. And we can keep going. 1 microfarad will give us 100 hertz, and 10 microfarads will give us 10 hertz. These values being the same. And that is approximately a 50% duty cycle, so it's going to be... And that, of course, goes into our Phi 0 pin. So that's basically what we're going to do, and let's get making. Okay, so I've gathered my bits. I've got a printout of the circuit schematic that I just knocked up in KiCad. And I'm throwing it about. Piece of Veriboard. 470 ohm resistors, 1K resistors, capacitors, some LEDs, a 555 timer, and some sockets. And here's a switch just in case I decide to put a reset switch in. So the logical way to do this is to have it going crossways like that. On this side, of course, obviously. Not particularly constrained for space. But we want under here a line of LEDs and resistors. The resistors for the data bus will go up here. The 555 timer will go up here. This is the pin that the timer is going to, so it's logical that they would line up. Something like that. And then we can start putting things on. Of course, I've got a ton of wire, because you can bet your doodads that it's not going to line up exactly how we want. So, for example, let us just grab some red LEDs. And I'm not worried about orientation at the moment. But you can see the closest we can get them is 2 apart. So we can't just go line to line to line to line to line, much as we'd like to. And of course we can't have them like that, because we need to cut the trace in between. So they're going to have to be like that. Unless I've got some different Veriboard, I'll have a quick look. Okay, what I think I might use is this. This is a user port prototype board for a Commodore 64 that we got previously from PCBWay. Now, in theory, I could take power off this and power it completely from the C64. You plug it in and then run the thingies. But if all the LEDs are fitted, and there's 13 of them, and they are all on, then that would draw something like 260 milliamps, and the user port will only supply 100, so that isn't going to work. So we will definitely still need to supply our own voltage, but we could build it on this. And in that case, it might be nicer to have it the other way round, just so that the LEDs are at the top. So I'll build it basically that way up. And then it doesn't really matter how that is joined because these are all discrete holes. So it means we have to wire everything, but that's fine. Let's tack this on and get going. So I'm going to use red wire for 5 volts and black wire for ground. Okay, I've put that socket in and I've connected those wires up. So let's put in our resistor network. I'm going to make that line along there VCC. Right, I think I've done it. I decided not to film most of it in the end because it was a lot of faffing about. So I've got a USB connector for the power, and a couple of pins there just so that we can check it. I've only put 4 LEDs on because that should be enough to see whether it's actually working. If we want to put the others on, we can do, but it's dependent really on the frequency. I've added a reset switch, and I've done this kind of switch because the pins for it were on the board, and that basically goes from the reset pin to ground, and it's still pulled up to 5 volts. So these are the pull-up resistors. So on the back it's just a mess of wires. I've used red and black purely for 5 volts and ground, and different colours for the actual signals. So these are the address outputs. That's the reset line. That's our clock. That's an internal connection on the clock circuit. So I've beeped everything out, and I'm reasonably confident that that is actually correct. All that remains is to try it out. And I'm not going to put one of these in to start with. I'm just going to put a 555 timer in there and see what frequency we get. So I will just show you that we do not have a short. Again, that is definitely not shorted out. We can go from, what is it, 2 and 4. 2 and 4. So that's good. Let's put a 555 timer in there and see what we get. Timer is in. Now I'm going to clear this detritus off the bench. Okay, now I've got a USB cable. It's USB A to USB C. So obviously the USB A end will go into my wall thing, and the USB C end can go into here. So let's see what we've got. So we'll start off by looking at volts. .09, that's good. Then we'll look at hertz. Pin 3. .50 kilohertz, 50-ish. I suppose that's not bad. We didn't know exactly what the values were going to end up as, but we are getting a signal out, and let's just look at it on the scope. Okay, it's not particularly square, but it is right. There we go. Hopefully you can see that. So let's measure. Clock 0 going in. 100 kilohertz, that's correct. It's not a 50% duty cycle though. But anyway, we shall see if that is actually going to work. It might do, you never know. So here goes my first IC. Let's take this one. So I've got the wristy on. Stick it in. Right. Here goes nothing. 3, 2, 1. Look at that. Now the reason it stops periodically is because this is just the high order address lines, and sometimes it's just going through the low order bits. And there we are. That is awesome. As you can see, the 6507s that we've tested have in fact all worked, and The NOP Tester that I've built here, I'm going to make available as a shared project. I shall lay it out onto a PCB, very similar to that. Keep an eye on the description for details and availability of that and a link. The circuit as it is laid out is running at 100 kilohertz for the 555 timer and the clock. Now you can slow that down, and I think that's about as many LEDs as you want at 100 kilohertz. Certainly adding more of those, you're not going to see them flashing. If you slow the clock down, then obviously more of them will flash, and the end one will take longer to cycle through. To do that, basically you just need to change the value of this capacitor, and every times 10 increase in the capacitance will basically divide by 10 the frequency. So this is 1 nanofarad. If you change that to 10 nanofarads, then it runs at 10 kilohertz. If you change it to 100 nanofarads, it runs at 1 kilohertz, and so on. So if you've got this far, thank you for watching. I hope you've enjoyed the video. Please check out my Patreon. My patrons have been scrolling up the screen. Now, I'd already edited the video and uploaded the Patreon version when these arrived. These have just arrived from PCBWay, and these are our 6507 NOP Tester boards. So let's take one out and build it up. I wasn't expecting these to arrive until after the video was out, so this is a little bit of a bonus. And I did just want you to be able to see what the final tester looks like. So rip it out. So this is the NOP Tester board, and on the back we've got a little table of frequencies. What I'll do is I'll build this up, and I'll do it off camera just so that, because we've gone on long enough. I'll put a lower frequency in here so that we can have more LEDs. And I've got plenty of red LEDs. I've got some barrel connectors, a few more thingies, and let's just build it up quickly. Here we go, it's built. I've put all the LEDs in and all the 470 ohm resistors, and I have set it to 1 kilohertz according to this chart, which is 100 nanofarads. Sorry, I have set this to 100 hertz by the chart on the back, which is 1 microfarad. So that is a 105. The only thing that I haven't got is the reset switch, because I ordered some in that form factor and they haven't arrived yet. Anyhow, let's plug it in and see if our... Okay, so let's put the wrist strap on. There we go, and try one of these 6507s. Let's just pick one at random, stick it in here, plug it in, and here we go. So once again, thanks for watching, and we'll see you next time. See ya.